Orchestra or band combines so many varieties of sounds. And what better way to learn the physics of sound than with music? First, you have to know all sounds are caused by vibrations. A vibration causes the air to move. That motion of molecules in the air creates sound waves. And musical instruments control sound waves. To make music, you want to control those vibrations. Creating standing waves is one way to control sound waves. Standing waves are produced by the interference of two traveling waves moving in opposite directions but appear to be standing still. Objects, when struck with a force, have a characteristic vibration, a natural frequency at which they vibrate. Let's take a look at some natural vibrations or resonant frequencies created by three different instruments: a stringed instrument, an open-tubed instrument like a flute, and a closed-tubed instrument like a clarinet. Even though we're dealing with sounds, which are longitudinal waves, we're going to use transverse waves to help us visualize areas of high and low pressures within a sound wave. It'll help you see how these waves interact. The lowest resonant frequency at which an object will resonate that produces the simplest standing wave is called the fundamental frequency, F sub 1. An object will resonate at other frequencies as well. These other resonances are what we call harmonics. The fundamental frequency is known as the first harmonic, and the harmonics above it, also known as overtones, are numbered F sub 2 and above. Now let's see how this applies to playing musical instruments. First, let's look at a stringed instrument, where the string is attached at each end. When the string is plucked, that creates a vibration that moves through the string and is reflected at both ends. Remember, anytime a wave hits a rigid barrier, like the ones created by the attached string on this violin and the musician's finger on the string, there will be a node at that point and at this point. The vibration of the string happens on a microscopic level. It is only thousandths of a millimeter between the crests and troughs of the standing wave created by the string. We'll magnify what the vibrating wave looks like so that you can see it more clearly. So pluck the string, and the first position of the string we see is the incident wave. That's the solid line. The wave opposite is the dotted line, and that's the reflected wave. To find the wavelength that corresponds with a fundamental frequency, what would be the most basic shape that would have nodes on both ends? Would it look like this? How much of a wavelength can be seen here? Remember, a wavelength consists of one complete crest and one complete trough. There is 1/2 of a wavelength present within this given length of string L. So mathematically, the wavelength equals 2 times the length of the string, L. The simplest standing wave shape corresponds to the fundamental frequency, written F sub 1, also known as the first harmonic. Each harmonic must have a node on each end, since both ends of the string are attached to a rigid barrier. But we could also have a standing wave like this, again with a node at each end, but now with a node in the middle. This is the second harmonic with one wavelength corresponding to the string's length. This is Jacob, our cellist for the day. Thanks for joining us, Jacob.
You're welcome.
Can you please play a fundamental frequency?
Sure.
And what about the second harmonic? Which is lower? Correct. The fundamental frequency, or the first harmonic. Within a harmonic series, the fundamental frequency will always be the lowest. The diagram now shows 6 different harmonics with the same string. All harmonics higher than the fundamental frequency will resonate when the wavelength is equal to 2 times the length of the string divided by the harmonic number. So the second harmonic's wavelength is equal to 2 times the length of the string divided by 2, which is just equal to the length of the string. The third harmonic's wavelength is equal to 2/3 times the length of the string. This pattern continues with each higher harmonic, where the wavelength is equal to half of the length of the string times n, which is the harmonic number above the fundamental. on stringed instruments are tuned to precise frequencies related to exact wavelengths. So when replacing strings, you buy specific strings for each series of notes to be played. And if you look at strings, you'll notice they're different from each other. Each one has a different and exact thickness and a mass to cover specific ranges of sounds or notes. And increasing the tension on a string changes the pitch or the note. So does changing the length of the string. So Jacob will pluck the A string, which, when properly tuned, has a fundamental frequency of 440.0 hertz. The length of a cello string is 0.690 meters. Since the wavelength equals 2 times the length of the string for the fundamental frequency, the wave velocity equation becomes wave velocity equals 2 times the length of the string times frequency, or 2 times 0.690 meters times 440.0 hertz, which gives us a wave velocity of 607.2 meters per second. Now bring on the wind. Wind instruments, like flutes and clarinets, also use resonance and standing waves to make beautiful music with lots of different frequencies. In both cases, standing waves must form inside tubes or pipes. If the tube is open at each end and doesn't have rigid barriers, the standing wave that forms will produce an antinode on each end. The fundamental frequency, which again is the first harmonic and has the simplest waveform, has a single node in the middle of the tube with an antinode at each end. Like the stringed instruments, the fundamental wavelength, or lambda sub 1, equals 2 times the length of the tube, L. The relationship between the wavelength and the length of the air column is the same for stringed instruments and for air columns that are open on both ends. And for all higher harmonics, lambda sub n equals 2 times L divided by the harmonic number, n, the same as stringed instruments. Likewise, since wave velocity equals wavelength times frequency, you can substitute 2 times the length of the air column for wavelength to find the velocity of sound through the air column for the fundamental frequency. The difference between a stringed instrument and a wind instrument is the temperature of the medium through which the wave is traveling, like air, for example. The temperature of the air changes the density of the air dramatically and can change the pitch produced by a wind instrument. As the air warms, the pitch of the flute actually gets higher. Now let's look at a wind instrument with one end closed and the other end open, called closed-ended. A clarinet is an example. Even though one end is slightly opened, where air is being pushed through by the musician, acoustically, it behaves like it is a closed-ended. By the way, when musicians want to change the pitch, that is the frequencies of any wind instrument. They change the length of the tubes by pressing the various keys. This changes the length of the air column, which changes the length of the harmonic wavelengths. In a closed-ended tube, like the clarinet, to get a standing wave, a node must be at the closed end and an antinode at the open end. The wavelength of the fundamental frequency is only 1/4 of a wavelength long. That means that the first harmonic, or fundamental frequency wavelength, lambda sub 1, forms at the length of the air column times 4. Because the antinode is at the open end and the node is at the closed end, each harmonic only happens with the addition of 1/2 of a wave, which means the harmonics are odd multiples, 1, 3, 5, etc. Those odd numbers are significant because you can see that the harmonics only occur when you have an odd number of fourths of a wavelength. They are called odd fourths. You find wave velocity and frequency the same way as the string and flute, which is velocity equals wavelength times frequency. But now the harmonic wavelength, lambda sub n, is equal to 4 times the length of the air column L divided by n, the harmonic number, which must be odd. And now you should know the physics of music and how it relates to standing waves and resonance.